Okay, let's just dive right into this explainer of chapter 3. We're going to take math from, rote calculation and turn it into this fascinating playground of patterns and mysteries. If you've ever thought math was just about memorizing times tables or staring at equations on a chalkboard, well, get ready because your perspective is about to completely shift. We usually think of numbers purely as tools, right? Things for measuring, keeping track of time, buying our groceries. But today, we're asking a totally different question about how they organize our lives. What if numbers aren't just for counting, but for playing? What if they're actually the foundational building blocks of games, puzzles, and these hidden codes that are just waiting to be cracked? So here's our roadmap for today. We're going to start with how numbers tell stories, then learn to spot hidden patterns, explore some mind-bending, unsolved mysteries, and we'll wrap up with how math actually gives you unbeatable winning strategies. All right, kicking things off with section 1, numbers tell a story, specifically looking at the height game. Now, what's really cool here is that these kids aren't just counting off sequentially like 1, 2, 3. They're actually revealing a hidden story about their heights, purely based on where they're standing in line. You see one child saying 1, another saying 1, and the tallest kid saying 0. Let's actually decode what this spatial code means. The rule here is brilliantly simple. Each person says the number of taller neighbors they have right next to them. So boom, you immediately turn a physical setup into data. If you have one taller kid next to you, you say 1. If both the kid to your left and your right are taller than you say 2. And if you happen to be the tallest one in your little spot, meaning neither neighbor is taller, you proudly shout 0. It's just a fantastic, really interactive way to see how numbers can code our physical world. Moving right along to section 2. Spotting the hidden patterns through visual mathematics. Take a look at the concept of supercells. These are specific numbers that are highlighted simply because they're strictly larger than all of the numbers right next to them. For example, that 626 up in the top row, that's a supercell because it beats the 577 to its left and the 345 to its right. But the 200 on the far left, well, that doesn't get highlighted because it's sitting next to that bigger 577. Finding these supercells is basically training your eyes to scan data for peaks and valleys, kind of like reading a topographic map. Okay, let's pivot to a totally new pattern with a quick challenge for you. Imagine you're a digit detective, and you have to write out every single whole number from 1 to 100. How many times would you physically write the digit 7? Think about it for a second. It's super easy to just quickly guess 10, right? Assuming there's about 1 for each block of 10. Well, if you guessed 20 times, you hit the nail on the head. And this shows us that even simple, everyday counting hides these surprising little frequencies. You've got your standard single sevens, 7, 17, 27, but then you hit that block of 70s, 70, 71, 72. And the real trick that trips people up? The number 77. You have to write the digit twice there. It's just a perfect reminder to look a little closer at systems that seem totally obvious on the surface. Which brings us to a totally different kind of pattern, one based on visual symmetry, palindromic numbers. Just like symmetrical shapes, these numbers have this unique property of reading exactly the same forward and backward. Honestly, they're hiding in plain sight in our daily lives. Like when you glance at a digital clock and it's exactly 10:01, or you're watching the miles spin by on your car's odometer. Recognizing them is just a really playful way to interact with numbers in the wild. All right, transitioning into our third theme, unsolved mathematical mysteries, and specifically, the Collatz conjecture. The Collatz conjecture relies on just 2 incredibly simple rules that you apply over and over to any starting whole number. Step 1, if the number is even, you cut it in half. Step 2, if the number is odd, you multiply it by 3 and add 1. That's literally it. Those are the only rules. You just take your result and apply the rules again, and again, and again. So, the crazy thing is that when you actually apply these rules, starting with a number like, say, 10, it cascades through these wild jumps, but it eventually plummets straight down to the number 1. Let's walk through it. 10 is even, so half of that is 5. 5 is odd, so 3 times 5 plus 1 gets us 16. 16 is even, have it to get 8, which goes down to 4, then 2, and finally 1. And once you hit 1, the rules just trap you in this infinite loop of 4, 2, 1 forever. So here is the massive, dramatic mystery. Does every single starting whole number eventually crash down to 1? Or is there some incredibly strange number out there that defies the rule and just escapes off into infinity? Mathematicians have tested this up to astronomically huge numbers using supercomputers, and so far, every single one collapses to 1. But the wild part? Nobody on Earth has been able to definitively prove that it will always happen.
It's a stunningly simple game with a profoundly difficult, totally unsolved mathematical secret.
And finally, we enter our last playground zone, games and winning strategies. This is where we look at the game of 21.
In this famous game, players race to exactly 21. The rules are super straightforward. You take turns adding 1, 2, or 3 to the running total. But if you play it enough, you're going to start to see a mathematical strategy emerge that basically guarantees your victory. You'll realize that to confidently win, you have to be the one to land on the number 17. Why? Because no matter what your opponent adds next, whether it's 1, 2, or 3, they leave you perfectly positioned to hit exactly 21 on your next turn. And how do you guarantee you hit 17? By hitting 13 before that. You're literally working backward using math to turn a simple game of chance into a guaranteed win. So why does all of this actually matter? Well, because finding those winning strategies, mapping out those supercells, and decoding that height game, that is the very foundation of computational thinking. It's this incredibly powerful process of formulating set procedures to use numbers to solve complex problems. When you're doing this, you're effectively training your brain to think exactly like an algorithm. As the chapter summary so beautifully puts it, the true magic of math is that the simplest questions often hide the most difficult, complex challenges. I mean, think about it. A child can understand the rules to the Collatz conjecture, yet the greatest computational minds on the planet still cannot solve its ultimate mystery. So now that we've explored the playful, the strategic, and frankly, the mysterious side of numbers through this explainer, how are you going to use them? Are you going to use them to build your own unbeatable game strategy? Or maybe you'll pose your own unsolved mathematical mystery? The numbers are yours to play with. Dive in and let's keep exploring.